Okay, 16.3, the fundamental theorem for line integrals. Okay, let me write the title for the people. For line integrals. Okay. So this section was spicy, huh? Oh no. 17, part A says, find a function f such that your vector field f equals the gradient of f. And then in part B, use that function to evaluate line integral over c of f dot dr. What does that integral represent? Work. Very good. Okay, who needed 17? Okay, Mustafa. So here's the vector field f, which is 2x, 4y. So they're telling us, just go ahead, find the potential function. You don't have to do all the steps to check if it's conservative, unless you feel like you need to practice those. Okay?
It wasn't conservative because it's not equal.
It should be conservative if you can find a potential function. Yeah. Okay, this is P. This is Q, yeah. What's del P del Y, Mustafa?
Oh, I see. Never mind.
0, right? And then if you check the rest of the conditions, right? There's 3 conditions, it's going to be conservative. Okay, so now to find the potential function, you need to find little baby f of x, y, such that what we have, this given vector field, is the gradient of f. So P, for a conservative vector field, is the partial of the potential function with respect to x, and Q is the partial of the potential function with respect to y. So we know fx is already 2x. So take the antiderivative with respect to x squared, plus possibly some function of y, right? There could be terms that involve y that you wouldn't see, because when you take the derivative with respect to x, they'd go to 0. And then similarly, partial with respect to y is 4y. So f would be 2y squared plus some h of x, because if you had terms involving only x and you take the partial with respect to y, they would go to 0. Okay, then when you put your potential function together, f of x, y, you just list all the terms that you got from all those antidifferentiations. If there's duplicate terms, you don't list them again. It's just like, oh, it's already accounted for. I already have it. So we have x squared plus 2y squared. Good?
I can just leave it like that.
Yes.
You have to add the c.
Okay, you don't need it, because if you add the plus c, then in part B, when you're trying to find the work, right,
Oh, we have to see.
it cancels out, because you end up doing potential function at the end minus potential function at the beginning, and you're going to have a c minus another c, and they cancel out. So whether or not you have it doesn't make a difference, okay? And then the end point was, oh, c is the arc of the parabola from 4, -2 to 1, 1. So then you're going to plug in, the end point is 1, 1. So you're going to have 1 squared plus 2 times 1 squared if you want to put plus c, minus, and then plug in 4 for x and -2 for y if you want to plug in the plus c, but I really wouldn't, because you see what happens every single time? And then from there you should be good. Yeah? Okay. So that one's done. And then 37, 38, 39, 40. Oh, all of the open and simply connected columns? Yeah, Kimberly, what's up?
So in the previous question, it was just find the potential function.
Yeah.
And it said that, or in the answer, it said like it had a constant. If it was just asking what is the potential, you want to stick with the constant?
I don't care. Because I won't usually just ask you to only find it. I'll ask you to use it for work. So it's okay. I don't care if you put the plus c or not. Yeah. Okay? In differential equations, we did put the plus c because it's a different context when you're saying like this is the solution to a differential equation. Okay, so you can, when you take DEs later, then you'll already know one of the sections. Yeah. Okay, so then let's do all of these. 37, so we have to determine whether it's open, connected, and simply connected. Open, connected, simply connected. I would recommend graphing all of them, okay? So 37, we have the region in the xy plane such that y is between 0 and 3. Okay, so are those lines where y is 0 and 3 going to be solid or dashed? Dashed. Now, it's hard to see a dashed line at y equals 0 because it's on top of the x-axis. So what I usually do to remind myself, I'll put like extra little dashed here so that my brain can see something and remember that it's there. And then y equals 3 is here. So the region is everything in between those two dashed lines, okay? So let's ask the question, is it open? Can you draw a disk around any point in the region that stays entirely in the region still? Yes, right? So it's open. Is it connected? Can you get from any point in the region to any other point in the region by staying in there? Yes. Is it simply connected? Can you draw a simple closed curve and contain points that are not in D? No. If you're in D, if the curve is in D, some simple closed curve, there's no way you're going to contain points in there that are not in D. There's no holes, basically. There's no holes. So it's simply connected. Okay. Let's look at 38 now. That one okay? Yeah. 38, f of xy. No, just xy. Why did I say that? Such that absolute value of x is between 1 and 2. Okay. So let's see, what does this look like? Absolute value of x equaling 2 would mean x is 2 or negative 2. And then absolute value of x equaling 1 means x is 1 or negative 1. But it's between those values. Okay? So here's how you're going to graph it. Is there any restriction on what y can be? No. So we're going to have a series of vertical lines where x is negative 2, negative 1, positive 1, and positive 2. Negative 2, negative 1, 1, 2. All of the lines will be dashed because the inequalities are strict. They're not inclusive. So dashed line here, dashed line here, dashed line here, dashed line here. Okay? Now where do you shade? In between them. Those two pieces, right? And then just check, is the absolute value of x for any point in those regions between 1 and 2? Yeah. Any point you pick here, any point, the x value is between positive 1 and 2. So that's obviously absolute value of x is between 1 and 2. And then any point you pick in here, the x coordinate is between absolute value 1 and 2 because the x coordinates are between negative 1 and negative 2. Yeah? Was drawing the graph hard?
Yes.
Yeah, I had to think about it right now for a second. Yes, Lucas.
So if there were solid boundary lines, then it would not open because then
We didn't even talk about that yet. But these being strict inequalities means they're dashed. Okay? So first, is the region open? Can you draw a disk around any point in the region and stay entirely in D?
yes.
Yes, it's open. Is it connected? Can you get from any point to any other point staying entirely in D? No. Is it simply connected? It can't be because it's not even connected. Okay? So not simply connected either. So if it fails connected, then you know it's going to fail simply connected. Okay? All right, 39. What? You like this one? X, y, such that 1 is less than or equal to x squared plus y squared is less than or equal to 4, and y is greater than or equal to 0. So what does this look like? The inequality x squared plus y squared between 1 and 4 inclusive is going to give us what? Yes, a donut. What's your favorite donut? Not that I'm bringing you any, I'm just curious.
Maple.
Maple? Oh. I'd like a good old fashioned. Or vanilla with sprinkles.
Boston.
Boston cream. Oh. Okay, hold on. I want it to look beautiful. No, that looks kind of screwed up. How's that? That's good, right? We're happy with this. Let me label it though. Right now it's a free floater. 1. You know what? It's not to scale, but who cares because we're labeling it. All is well. But then also we're saying y is greater than or equal to 0. So actually it's only here. Yes? Okay, so let's erase this piece here. Just come in, color all this in. Okay. And we're including the boundary. Got it? Yay. Pink and green do go nice together. Okay, so is the region open? No, anytime the boundary is included, it can't be open. Because if you take a boundary point and you try to draw a disk around it of non-zero radius, you're going to be outside the region. Okay, so no way. Is it connected? Can you get from any point in the region to any other point in the region staying in D?
Yes.
Yes. Is it simply connected?
Yes.
Yes. Basically, ask yourself, are there any holes? If there's no holes in the region, then it's a yes, as long as it's connected.
So if it was a full circle, it would have been not something.
Right. Very good. So if they didn't add y greater than or equal to 0, then it would not be simply connected. Very, very good. Yeah, Kyle.
Why does it becoming a full circle shift though?
Because if it was a full circle, then we would include all this. And I can draw a simple closed curve that stays entirely in D and contain points that are not in D.
But so it wouldn't though, even if you cut it in half.
No, because now if I make a simple closed
it wouldn't
curve,
be closed. Okay.
yeah, it has to be a closed curve, and the closed curve has to be entirely in the region.
Okay.
Yeah. Yeah. But there's no way to exit D and have a closed curve. Yeah, exactly. Uh-huh. Fun, right? No? Oh my God, when we were learning limits again, like in upper division math class, did you guys do delta epsilon proofs in your Calc 1 class a little bit? So then they like generalized it because that's like for functions of one variable, right? So that's like 2D, and you talk about like n-dimensional space and like accumulation points, and you have a disk around things. It gets kind of funky, so you have to visualize a lot in this way, in these terms and things. All right, last one, 40. Yeah? Ooh, 40, so spicy. Okay. xy such that xy is not equal to 2, 3. What did 2, 3 ever do to anybody? Poor 2, 3. Okay, so I would just draw a little open circle here at 2, 3, and then just shade everything else, okay? So is the region open?
No.
Why not?
Well, you can put a dot next to that hole.
And you can still make a disk that stays entirely in D of non-zero radius. You just have to make it very, very small. Yes, you can get as close to the point as you want without being at the point, and then I just choose a radius even smaller than the distance I am from the point. As long as you're not at the point, you could draw a disk around it and still stay entirely in the region. It's like, have you heard, think about it this way. If you always eat half of something, you're never going to eat all of it. Like if you get a piece of cake, you're like, I'm only going to eat half. And then you're like, okay, I'll only have half of that. And then I'll only have half of that. And you only let yourself have a half. You'll never finish it.
Achilles and the tortoise.
Yeah. Okay, so it's that idea. You can get as close as you want to 2, 3, but you're still not at 2, 3, right? You're still in the region D. Can you draw a disk? Yeah, just take it smaller. Take it half of whatever your distance is from D. And you can draw a disk around wherever you are.
It's just like a boundaries.
Yes, exactly. Yeah. Okay, is it connected? Can you get from any point in D to any other point in D staying entirely in D? Yes. And then is it simply connected?
No,
No, why not?
there's a hole, right?
Right. It's a small hole, but it is a hole. So not simply connected. Okay.
If you ask for like proof or like to explain why all for simply connected, you just say like is it habitable or not?
Yeah, that's the, but I'll make sure also it passes connected first.
Right.
Because we looked at, let me go back. This one was not simply connected. It can't be because it's not even connected. But I don't think about does it have holes or not at this point because it failed connected. Okay? Just like, I don't know, I always think of it this way. Don't ask yourself if something is one-to-one if it's not even a function. Don't look at the horizontal line test if it doesn't even pass the vertical line test. Do you remember those dangerous days, like from pre-calc maybe? Okay. All right, that was it? Yeah, okay, so tomorrow we'll do Green's theorem and 16.4, 16.5. And then Monday we can do 16.6, 16.7. And then Tuesday 16.8, 16.9. Wow, this is aggressive. But then we get 2 days of review. Okay, I'll figure out the review assignment over the weekend.
Okay.
Thank you.
Yeah, it'll just be the practice test because you'll have just done the chapter 16 homework. Do you need to redo any of them? No, I think we're good. Okay. Don't forget to like, subscribe, and follow me on Instagram and TikTok, Math with Professor V. I'll be back sooner than later. Mwah.